Okay, I think we're going to go ahead and get started. I know some people are still coming in. No worries, just come in and find a seat. So glad to see you all here. My name is Ebba Segerberg. I'm the Senior Associate Dean and Chief of Staff in Arts and Sciences, and I am delighted to welcome you to the Spring 2026 Dean's Distinguished Lecture. In a few moments, we'll have the pleasure of hearing from Xuming He, Chair of Statistics and Data Science, and the Kotzubei-Beckmann Distinguished Professor, as he speaks about statistics for AI or AI for statistics. I may have that wrong, the other way around. All right, after the presentation, we'll have time for a Q&A. That's going to be moderated by Aaron Bobick, Dean of the McKelvey School of Engineering and the James M. McKelvey Professor. And then we invite all of you to join us afterwards for a reception in the entry space just outside the auditorium. It'll be over to our left. And if you have not already done so, please take a moment to silence your cell phones or any other devices before we begin today's program. Our next speaker is going to be the host of today's event, Feng Sheng Hu, the Richard G. Engelsmann Dean of Arts and Sciences, and Lucille P. Markey Distinguished Professor in Biology and Earth and Environmental and Planetary Sciences. Many of you already know him, but for those of you who don't, I want to give some quick highlights. As a scientist, he is widely recognized for his innovative research on long-term ecosystem dynamics in relation to climate change. In addition to his many publications and grants, he has received a number of scholarly accolades, such as being named a Packard Fellow, Fulbright Scholar, and a Fellow of the American Association for the Advancement of Science. Prior to joining us at Washington University, Dean Hu was at the University of Illinois Urbana-Champaign for many years, and he served in a number of leadership positions there, including as the Harry E. Preble Dean of the College of Liberal Arts and Sciences. Since arriving here in July 2020, yes, in the middle of the pandemic, Dean Hu has focused on implementing a bold strategic plan for the future of arts and sciences. As a result, over the past few years, Arts and Sciences recruited a large number of outstanding scholars, including Xuming He, who became the inaugural chair of the new Department of Statistics and Data Science, launched by Dean Hu in partnership with Dean Bobick as part of his strategic plan, something you'll hear more about shortly. Under Dean Hu's leadership, Arts and Sciences has seen record rates of external grant funding and a range of new initiatives to spark convergent and innovative work in both research and education. And now please join me in welcoming Dean Hu to the podium.
Thank you so much for that kind introduction, and good afternoon to all of you. It's wonderful to see so many of you here for what is now our third Dean's Distinguished Lecture in Arts and Sciences. As you may know, this lecture series was created as an opportunity to showcase our highly accomplished faculty in arts and sciences, and for the campus and community to learn from some of the brightest minds in arts and sciences. We previously heard from world-class scholars in poetry and political science, and today we will hear from one of the world's leading statisticians, Xuming He, who we are fortunate to have as a colleague in arts and sciences. Xuming is the Kotzubei-Beckmann Distinguished Professor and Chair of our new Department of Statistics and Data Science. I think you all know this. We are at an inflection point in higher education in the United States, which makes this the perfect moment for a gathering of this nature, where we celebrate scholarship and explore the forces that shape the world around us. Higher education faces many challenges today, but there are also bright spots and many opportunities. Fields leading and experiencing exciting growth due in no small part to our passionate and distinguished faculty. And tonight, I'm delighted to share with you one of these visionary scholars. Now, just a few years ago, in close collaboration with the McKelvey School of Engineering, we set out to launch a one-of-a-kind department of statistics and data science that will leverage the power of big data to confront society's most pressing challenges. Aaron Barbic, the Dean of McKelvey Engineering, who is in the audience sitting right there, and I knew that this world-class department would require a world-class leader, someone with outstanding credentials and the ability to attract field-leading scholars. And for those of you who don't know, if you feel like there's a very important job that you need somebody to do and that you cannot do yourself, you choose somebody who is smarter than you are. And what I did is I managed to convince Dean Barbic to be the search committee chair. And so, thank you, Aaron Barbic, for this important position. And so Xuming was the search committee's unanimous top candidate. And I think you had something like 10 people on the search committee from Arts and Sciences, McKelvey Engineering, and the medical school. So Xuming is a globally known statistician, educator, and leader who prioritizes interdisciplinary research. And we're so fortunate to recruit him from the top-ranked University of Michigan statistics program. Under his leadership, our Department of Statistics and Data Science has grown exponentially. In less than 3 years, we have hired some of the field's most talented data scientists and statisticians, including environmental statisticians, Bo Lee from the University of Illinois, Urbana-Champaign, and Joe Guinness from Cornell University. We also recruited Xiaofeng Zhao, who is sitting over there, a leading time series expert, also from University of Illinois, Urbana-Champaign. I don't know why that school kept popping up. I'm sure it has nothing to do with me. But we also have a stellar cohort of assistant professors from elite institutions all over the country: Harvard, Princeton, MIT, Stanford, Rice, what did I forget? A bunch of incredible institutions with faculty launching groundbreaking research and collaborations across campus. The department has already established national prominence as a data science powerhouse that will catalyze digital transformation across fields of artificial intelligence, public health, sustainability, and climate change. We owe much of the department's early success to Xuming. As you can imagine, his career is one of distinction. He earned his PhD in mathematics and statistics from the University of Illinois, Urbana-Champaign again. Taught at the National University of Singapore, returned to UIUC as a professor, and became an endowed chair of statistics at Michigan before moving to WashU in 2023. Xuming's leadership in the field of statistics is practically unmatched. Among a long list of accolades, he is the immediate past president of the International Statistical Institute and an elected fellow of a number of professional societies, including the American Association for the Advancement of Science, as well as the American Statistical Association and the Institute of Mathematical Statistics, where he was awarded the Founders Award and the Carver Medal, respectively. But what makes Xuming a perfect fit for WashU is his interdisciplinary approach. He's a champion of applying statistics and data science across many fields to tackle problems and find solutions. From biostatistics to climate change to social-economical analysis, this transdisciplinary thinking is exactly why our Department of Statistics and Data Science is well on its way to being one of the best in the world, despite the fact that it's only 3-year-old. I know you will feel the same after hearing from him speak this afternoon. So with that, please join me in welcoming a colleague and my friend, Xuming He.
Well, I'd like to thank Dean Hu for the very generous introduction and affirmation of our new Department of Statistics, Data Science at WashU. Also, I'd like to thank him for inviting me to speak here today, and it's always a distinct honor to be part of this distinguished Dean's lecture series. Being distinguished is always good, I suppose. Of course, I also like to thank every one of you here in the audience, including those who are participating online, to take your precious time and to be with me today. So my talk today is about AI and statistics. Abby could put it either way, AI for statistics or statistics for AI. It's really not a question. It's something that I have been thinking about, and I'm sure quite a few of you have been thinking about. These days, you cannot escape AI anymore, right? Just a recent Wall Street Journal article reported that industry in the United States, some of the heavyweights, are spending a lot of money. They projected about $700 billion just for the year of 2026. And if you only look at the four of the leading firms like Microsoft, Meta, Amazon, and Google, they came to about $670 billion. I think this is probably the biggest investment the corporate America is making in a single year on a single theme. Of course, you can say corporate America is greedy. Who knows whether they will be successful or not? Money is just money, right? But if you think again, what is more important than human health? So let's take a look at how people are using AI for health-related questions. A very recent report from OpenAI, and together with a recent report by American Medical Association, they show that 40 million people in this country use ChatGPT every week to answer health-related questions or healthcare-related questions. 40 million, how big is that? Think about total US adult population, maybe I don't know the exact number, but somewhere around 250 million. So we're talking about 1 in every 6 adult in this country quiz ChatGPT, not to count other chatbots and so on, every week. US physicians, the doctors that we trust when we have a medical problem, 2 in 3 US physicians used health AI in 2024. That was like a 78% jump just over the year of 2023. Now, this is happening despite the fact that we all still have a lot of questions and reservations about the reliability of large language models as medical assistants. I put that there, one of the very recent articles, I think just went online a little more than 2 weeks ago, studying the reliability of large language models as medical assistants. This world is not perfect, and there are a lot of concerns and issues when people rely on AI for health. Well, we should talk something closer to us about science, right? So AI has been around for a long time, especially if you think about the earlier generations of AI. But 2022 seems like a new beginning, right? Especially for many of the people in the audience who are young enough, and you may not even remember, when we were talking about the first generation of AI back then. But starting from 2022, maybe because of ChatGPT, people have approached AI with disbelief and amazement. So 2023, 2024, things happen very, very quickly. Every week you see headlines, some breakthroughs and amazing things happen, right? And a lot of people are saying that 2025 is really a year for coding. Right? So now I think coding has been changed fundamentally forever. If you read a very recent Nature article titled Science in 2026. The article is basically trying to say or argue that we are now shifting from generative AI to agentic AI. And that whole process is going to bring huge things to science and scientific discoveries. So a lot of people are saying that 2026 will be a year of AI for science. Now, if you trust my prediction, and my prediction is just going to be as good as yours, 2027 is going to be AI for teaching and learning. A lot of things will come to campus. We will see profound changes that we have to embrace, we have to adapt to on university campuses, whether you like it or not. Now, the title of my presentation is AI for Statistics or Statistics for AI. This is not a question I'm asking, right? So this will be a false dichotomy. It's not a question I'm asking. If you look at the number of degrees offered by universities in this country, you see two plots, two graphs here. On the left, it is the degrees in statistics. On the right, I think it adds up several degrees, like majors, including computer science, computer engineering, and information science. They are typically considered to be part of the majors that are highly related to AI. You can see the same kind of trend. If you look at the graphs a little more closely, from say 2010 to 2024, the number of undergraduate majors in statistics rose about 500%, five times. A similar trend actually happened in the other areas with computer science, computer engineering, and so on. So everybody is embracing AI. Now, whether the trend will continue at this rate, nobody probably knows. Usually it will start to slow down a little bit and so on, but this has happened so far. A major in AI probably didn't exist until around 2022, when MIT actually started to offer this degree in AI and decision making, and in just 3 years, this major now is the second largest major at the MIT, just after computer science. I guess computer science is still way ahead of this. Dean Barbick is here. Maybe he will later on tell us whether a similar degree will start soon at WashU. Now, obviously, I'm not going to spend a lot of time talking about AI. A lot of you probably know more AI than I do, and I think that the reason Dean Hu asked me to speak here today is to provide more statistical perspectives of the AI. So how do we talk about statistics and AI together, right? Well, if you think about statistics as a discipline, this is really trying to make use of data and model together to understand things, to understand what's going on, and also to help people make decisions, whether it's a prediction or other decision-making process. And what does AI do? Almost the same thing, except maybe it's doing this at a larger scale, pushing things faster, maybe with less rigor, but certainly relying more on computing resources, computing technology, and a few other things. So from the very beginning, maybe you can see that AI and statistics tend to go hand in hand. So I'm going to mention this 2001 article published in Statistical Science by actually a very controversial statistician at the University of California, Berkeley, Leo Breiman. So he spoke, actually, he also wrote this article, very direct and very controversial at the time. He said that in statistics, we use data and models, right, and try to let them work together and help us. There are two cultures at that time. One is to model data using a probabilistic law or stochastic generative process. And that was the dominating culture in statistics. Okay? You give me a data set, I try to model in some way and try to help you get some answers. But there's another culture that was just starting to become more prominent. It is the algorithmic modeling approach. That is, you view statistical analysis simply as an algorithm. When you have data, especially when you have big data, what are you going to do with it? Well, you let an algorithm take over and put the data in, use that algorithm, and to get the results. So this is another way of thinking how statistics help people analyze data. And Leo Brahman was saying at that time, 25 years ago, right, statisticians were basically too conservative, too timid. I think this was the word he used, but not in an article, in one of the conversations, to embrace this shift from one culture to the other. Well, he's probably not 100% correct. I think we still need both. Both approaches are very valid even today, right? The stochastic modeling, you think about how the data are generated and so on with the probability structures, and simple statistical models are still very, very useful in many areas of applications, but the algorithm-based approach, that new culture has also taken off. And that kind of converges with what is happening in AI. So this is how really I view the relationship between statistics and AI. So for the rest of the day, I'm going to really talk about two things where I feel like the AI has really pushed statistical research into new frontiers. On the slides, I said AI is revolutionizing statistical research and applications as well. There are many, many aspects of it, but I will just focus on two themes. The first one is about data source and data format and whatever data that you can have. Now, I still remember when I was a graduate student learning statistics, right? What kind of data we had? Data were basically just a set of numerical values, usually, maybe a few dozen numbers. That's already a decent data size. Otherwise, we didn't know how to deal with it. Today, data come in all different sources and formats. Right? Talk about high-dimensional data. We talk about data in terms of networks, like social networks, text, okay? Images, voices, and all that stuff. That's part of the data we deal with every day now. We also talk about data which sometimes are so big or sometimes so sensitive that you don't really have direct access to. So data are stored in multiple places, and some of that's not really available to you. How can you do data analysis in this distributed or decentralized framework? There are also more and more synthetic data coming our way. Usually when we talk about data needs to be collected by human experiment. Either you design an experiment and you get heavy human engagement in the process, or you collect data in a lab, in a chemistry lab or biology lab and so on. But these days, a lot more data are actually generated by AI, one way or another, or at least to some extent. I'll return to that later. So the different focus on data is one big change, one big shift in statistical work today. So the way I will phrase it is that there has been already a big shift in how we do statistical work. Right? Traditional statistical work uses one data set, like if you do a survey and then just analyze the survey data. If you do a randomized control experiment, you just analyze the data that you have collected so far. So one data set, usually for one purpose in one study, often by one statistician. So this is how statistical work was done many years ago. But today, we're really talking about multi-source, many different types of data putting together, maybe answering questions in multi-dimensions. And sometimes you will be answering questions that you didn't ask at the very beginning. So even the questions, the goals are adaptive in the process. So you may have administrative data, internet data, data from drones, from satellites, and survey data as well. You often need to put data of different sources together to get a better sense of what's going on. So this, what I call data fusion and data integration. And this is, I think, a new norm now in statistics. And I certainly cannot say, oh, this is all due to the emergence of AI, but this is definitely related to the rapid development of AI in recent years. So this is the one thing. I'm going to spend a little more time on the second part I'm going to talk about is that AI is really pushing statisticians to think about new insights, new methodology to tackle important problems of the day. I'm going to start with a toy example. This is a toy example. You see the plot, a scatter plot. We call it a scatter plot in statistics. The vertical axis is income of an individual, okay, but on log scale. And the horizontal axis is the age of the person. Now you see, I hope you can still see that those solid circles, right, there are about 20 of them, they were income data together with age information for that person. They were collected, verified, and they're good data in the traditional sense. If you ask to understand the relationship of the income distribution, how that changes when people get older and older, when people age, you might say, okay, maybe fit a linear line, and linear regression is what we do all the time, and this is probably the one most popular tools out there. You only have 20 points, because getting people's income is not as trivial as getting people's age. Right? Now, you might notice that on the horizontal axis, you see many, many red dots. Those red dots represent information for many, many people here. I don't know, thousands of people here with age information, because age information is much easier to get. Here's one question. To help us analyze how income changes with age, do you simply rely on those 20 observations I have collected, or you also try to make use of other information you have available? There is I would say, a century-old wisdom in statistics. Right? It started from the likelihood principle, the likelihood popularized by R.A. Fisher about 100 years ago. If you believe in that, you take, let's say I have a linear model to tell us the relationship, to characterize the relationship between y and x. Y is the vertical axis, x is the horizontal axis, y is also called the outcome, x is called feature. And this plot tells you, okay, a linear relationship might make sense for the data that I have seen, right? And also you're going to assume that y given x has a normal distribution. Again, this is the stochastic component, right? The modeling, how the data are generated. If you do that, then the likelihood principle will tell you that you only need to observe the data, those 20 points. All other information, like age information from 2,000 people, is going to be irrelevant. In fact, I remember this example because when I was a student, one of the professors actually made this as like homework problem. Did you need all these extra observations on ages in this analysis? And of course, at that time, the answer was no. They're irrelevant. Fast forward 50 years, right? About 50 years ago, now people start to like this transductive inference, where now it's really popularized by a lot of people in computer science when they start talking about semi-supervised learning. I'm not going to really get too much into semi-supervised learning, but the idea is, well, actually, the data just about ages or these featured information might be very useful. Okay? Or I switch to another toy example, as you see here. Let's suppose that you have a lot of houses located along a river, and you can clearly see one subdivision on the top and another subdivision at the bottom. Suppose I'm going to analyze property prices. Okay, how much a particular house can be sold or can be appraised. And I only have a few observations, like I send appraisers to see their values, and I only have 3 blue dots. These are the 3 houses. The appraisers have come back with values. They all sell for over $1 million. And then I have how many? 6 Houses in the lower half, right, the appraisers came back and said, oh, they were all less than $500,000. Okay. Now, if you're going to use this data to try to predict another house that you have not seen, maybe the one, if you can look at this one right here, you might think that because this is closer to the red one, and then this is a relatively inexpensive house. On the other hand, if you know these are two subdivisions, if I have the feature information, I don't have the housing prices, you know that maybe there's one subdivision right there, they tend to have more expensive houses than the other subdivision, and that information can help you define boundaries and help you do prediction and other statistical analysis. Okay, obviously, this is a made-up story, but this graph was, if you take this graph to a machine learning class in McCovey, everybody will probably recognize that. So let me come back to this income versus age example, right? I have 20 observations, real observations, and I have ages for many other people. Now, these days, right, if I know somebody's age, maybe if I know a little more, like where this person lives, or what profession, right? Is it a professor, or as a banker, or a data scientist? You can predict the income of that person. Not very accurately, obviously, with very limited information. If you plug into any AI platform, like ChatGPT will give you a prediction. Okay? In fact, I tried a few of the people I knew, and I got 2 or 3 variables of that person. I plug into ChatGPT and ask them to do a prediction. The predictions were pretty good. Sometimes not, but overall pretty good. Maybe not at individual level, but definitely at the population level. And then now you can see the AI predictions of all these red dots. I lifted the red dots from the horizontal axis above, right? These were all predictions of ages, not very accurate for each individual, but clearly tells us a trend. Income does not go up linearly with age. Of course, we all know that. So this toy example is trying to tell you that now in statistics, we have to think differently, right? We have data that might be generated or predicted by AI, not directly available through human experiment or lab experiment, but those data can be very useful. So this comes to what I talk about, the synthetic data, right? Synthetic data becoming very common nowadays. Generally speaking, I would say there are 2 types of synthetic data. One type has the purpose of hiding information. This is often the case like in medical research, okay? You have data, but the data are so sensitive and private and need to be confidential. Or in business or in government entities where the data cannot release the real data, but the data are so valuable for research and other purposes. So people will try to generate synthetic data from real data, and hopefully the synthetic data has the same characteristics, statistically speaking, has the same characteristics as the real data. And one example is MD-clone. MD-clone is now publicly available. This is really mainly for healthcare data. Okay, so if you are part of WashU, you may not be able to get the real medical data from our School of Medicine, but you very likely, if you ask them, they will give you some synthetic data generated by MD-clone. So I'm not going to talk too much about that because I'm not speaking to medical school, right? There's another real purpose of having synthetic data. It's not to hide information, but to add information. Now this is basically the toy example I was using. I add information by asking ChatGPT to predict income of these individuals. And the example I put here is if you want to quantify the deforestation in the Amazon. I think Amazon is a lot of damages, right? That I think people were talking about almost 20% of the forest in Amazon no longer in good shape. That's a very serious matter. But how do you quantify that? Well, obviously you can send people there and to take a look and get a close, reasonably accurate measure of the deforestation. However, we have satellite images, right? Remote sensing technologies these days, very advanced and very affordable. Satellite images will tell you roughly how much damage has been done in many, many areas. And obviously not very accurate, but that's useful data. These are, now I'm calling them synthetic data because it's not just generated by a machine with no reason, but it's based on, say, satellite data. How do you incorporate that additional data or synthetic data into your real data analysis? I like to mention this 2023 article in Science. This was, this has how many authors? 5 authors, but if you look at the first 2 authors, Angelopoulos got a PhD from engineering, and then I think did a postdoc with statisticians. And the second author, Stephen Bates, I think he got his PhD in statistics and did a postdoc with somebody with a computer science background. So I like this is a good example of people cross fields, right? Cross training, maybe a PhD plus a postdoc with this kind of cross training can lead to great things. So this article really proposed a very nice framework for performing statistical analysis and valid statistical inference when experimental data are supplemented by synthetic data or machine-generated predictions. Now, this was 2023. A lot has happened after that. I'm not saying this paper represents the state of the art in this area, but this is certainly for something that you might want to read about. Okay? A lot, if you want to know more, you may be able to ask some of my postdocs who are actually here. They're really doing work in this area as well. And another nice thing about this article is that they talk about, they provided many examples, including those from proteinomics, astronomy, genomics, census analysis, ecology, and a few others. They try to demonstrate how this principle, this framework, can help people do data analysis when you couple, I would call it real data with synthetic data. Let me just spend maybe less than 1 minute to try to tell you why this idea works. And this is a very simple idea conceptually. Conceptually, it's a very simple idea. If you just go back to this linear regression model that I was talking about, you have y is linearly related to x, and I'm interested in the slope parameter b, right? How fast income is growing with age in that example. You have what people now call label data and unlabeled data. Label data are the ones with real observations, human data. And I use subscript L for label. So I have X and Y both observed for the label data. Unlabeled data with subscript U for unlabeled data, I have X but no Y. However, I have some way, some magic, some AI tools to help me predict Y. So now I have predicted Y for unlabeled data as well as the predicted Y for the labeled data, right? So usually unlabeled data come to you much more cheaply. Right? It's much less expensive. So you have a lot of unlabeled data, and then you can do statistical analysis on that. If you just do that, you might be very wrong because the predicted values are not the same as the real values. You could have an issue of variability, but also a bigger issue of bias. Okay? The results will be very biased. So how do you correct the bias? That's the main question. Well, you can correct the bias by looking at the label data, because for the label data, you have both the real observations as well as the predictions. If the predictions are off, you can see how much they are off. So if you can use the label data, both in terms of the real observed values and AI predicted values, let's say, just contrast, okay? That will provide a way of quantifying the bias. And then you can use that to calibrate the statistical analysis applied to the unlabeled data. So I hope that this is just simple enough for a lot of people actually to understand the basic concept. Now, the concept is very simple, and it can be used in many, many different areas. That's why I say this is statistically versatile. Of course, it cannot be done automatically. Okay? You still need statisticians to help you. Because in each individual setting, you need to understand how you characterize the bias and how you use that to calibrate the statistical analysis with unlabeled data. So it's not an automatic thing. The AI cannot do it right now yet, at least. Why I spend more time on synthetic data than on real data? Well, that's because synthetic data are on the rise, okay, whether you like it or not. Now, one I think business consulting firm actually predicted that by year 2030, majority of the data you see or you may be using will be synthetic data, at least partially synthetic data. And you may not even realize it. Sometimes you download data from the web or you obtain data from somebody else. You might not even know. These are synthetic data. Like Amazon, Uber, they release a lot of data on the web, and many of them are synthetic data. And if you don't look carefully, they look like real data. It may be okay for basic research purposes, but you still have to be careful, because if you really make decisions based on those, you need to apply the correct and appropriate analysis for that. And this is another challenge, actually, for many of us, because we sometimes don't know whether we have synthetic data or not. And even if we know, we may not know how the synthetic data are generated or how people get them. So a lot of things could go wrong. Due to time constraints, I'm going to go through them very quickly. The AI predictions might be wrong. How do AI do predictions? Well, the models are trained from other data. The other data may be biased, and those biases will be amplified in this process. There's a big issue of missing so-called black swan events, these rare events. AI models tend to be pretty good in simulating or emulating typical cases, but they often go very wrong for extreme cases. We also know that if people keep using synthetic data to train AI models and iterate in the same way, you eventually get something completely wrong, and this is now called model collapse. And synthetic data may provide a measure of association, but often masks causality, and causality might be something people are really interested in. So there are a lot of challenges and risks there. And I will tell you my personal story. Just a few months ago, I took a Waymo in another city, and Waymo was driving very cautiously, very carefully. I was very happy until it just stopped in front of my hotel entrance, where the hotel entrance somehow was very narrow. And somebody must be a hotel guest, maybe not very careful enough, dropped I thought it was just like maybe a bag from a supermarket, right? Just some stuff dropped on the road. And Waymo stopped right in front of it, waiting for this to disappear. And of course, it didn't, right? And Waymo kept waiting and waiting. I thought I could just, get out and remove this bag from the road, but I didn't know how to do it. Eventually, I had to force quit. There was an option in Waymo car. You can say, "Oh, just let's stop here." I will get out, and I got out. I removed the bag, but the car drove away. But fortunately, I was already at the hotel. So this kind of tells you these edge cases, it's a challenge for AI. And we all know that ChatGPT can perform very well on standard medical exam, but not very well for some of the nuanced diagnosis. In medicine, you still need to trust our doctors. So as statisticians, we really need to make sure we are helping others, and we are leading the efforts to develop trustworthy data-driven analysis with synthetic data. So that's my call based on what I have been talking about. And that requires teamwork. Right? You need statisticians, you need people who know the domain knowledge, the experts with certain knowledge in there, and you need a computer power altogether. So to me, statistics is data plus science. So you need data, you need some domain knowledge. Now, of course, you also need computing power. But you probably can say the same thing to AI, right? So that's why I'm very proud to say that, as Dean Hu referred to a little bit earlier, that this relatively new Department of Statistics and Data Science, now we have great faculty. Some have been here for a while, but many just joined us in the last couple of years. And then more coming this year, this fall. The department is probably more AI ready than most other Department of Statistics and Data Science in this country. Partly because we recruit more than half of our faculty just in the last couple of years. Our faculty are experts in many areas fundamental to AI research and applications like causal inference, the Bayesian computation, machine learning, reinforcement learning, uncertainty quantification, and I'm not going to read the whole list. So we are in a great place, and I'm sure my faculty are also very happy to collaborate with other people on campus. So to conclude, I'm not going to address the question of AI for statistics or statistics for AI question, but I will say AI and statistics are really flirting, and not just flirting with each other, they are actually quietly walking towards a wedding. Thank you.
There it is. That was great. For those I've not met, I'm Aaron Bobick from McKelvey Engineering. I'm not really sure why I'm here because I think Xuming could do this just by himself really well. But we do have a bit of time for some questions, and even though I don't really need a mic because we're streaming this, I'll use a mic, and I guess you'll have to use this mic here. So we'll take questions. All right, I've got some pre-loaded questions, but presumably I'll use one now and et cetera. So there was one question that was brought out that I think you already addressed, which is sort of the will statistics survive as a discipline, right? And so let me frame it another way. So you talk about statistics, your statistics groups being AI ready. So if somebody had done a whole bunch of statistics 20 years ago, but now want to be in an AI-ready statistics department, how is the discipline different from the perspective of someone sort of learning statistics and moving forward in it?
Yeah, thank you. Well, this is the good news is most of our faculty are relatively young, so they did not have that problem. But for people like me, right, who were trained almost 30, 40 years ago, yes, there is a big challenge that how we adapt actually to this new world. I don't think people need to do much as long as they keep their eyes open and they are willing to work with others. Working with others is the secret recipe. Well, not secret recipe. It's the recipe. Yeah. If you just sit in your own office, talk to yourself, and think about, I mentioned some of the examples, some of the training that I got. This great training I got, obviously, you might be lagging behind. So you need to talk to other people, and especially the younger generation. Then it's easy to catch up because a lot of fundamental tools do not change, right? A lot of tools that we learned many years ago are still very useful today.
One thing, one of the things that attracted both Feng Sheng and I, Xuming wrote he helped write a very important white paper about 7-8 years ago now, to the statisticians, basically saying that if we don't get involved in machine learning, A, they're all going to leave us behind, and B, they're all going to do really lousy statistics. And I think that insight of that the way statistics has changed is you now have to talk to other people, I think is fundamental. And those of us in the machine learning world would love to not do lousy statistics. So that'd be great. So we have a question over here.
So my question is about educating the public at large. So you're talking about some of the tools in statistics have been the same, and there's not really that much new under the sun. Something that is not new under the sun is educating the public about probability or margins of error or confidence. So how do you see that percolating into AI? So when you ask a question of AI and you get an answer, how can that get a margin of confidence, some sort of indicator of trustworthiness that the person who's going to act like on health outcomes can be somehow confident that they can trust what is coming out? How do you see statistics informing that process?
Yeah, thank you. That's a great question, right? So, as a part of the genes, in statisticians, we often think about how to quantify uncertainty. A lot of answers that you got from AIs, there's what we call certainty illusion. Is that right? They give you an answer, it sounds very certain, but not necessarily true. So I think this is a challenge for statisticians. People like me were not trained for public speech, right? So we need to think about how to use our professional, expertise, statistical expertise, and then to make sure that these things are appreciated by people outside our own field. Now, partly, I think our own research needs to also address some of those questions, like uncertainty questions. Also, how to explain this to other people. Instead of using technical terminology, you may need to relate to others. I think the only way, at least for me, to relate to others is to understand other people's languages. So this collaborative environment, when you talk to people in other fields, you learn their language as well. Gradually, you will pick up, the common language that people outside statistics use, and that's where your expertise becomes more helpful. I actually feel whenever I talk to people, people tend to trust statisticians. So it's not like they are shunning us, and it's a question of whether we are willing to talk to people.
Yeah, so I have a related question, and it makes me think of like how we're going to be educating our students, especially in sort of basic statistics. And I wonder if you see the change going from teaching students how to derive statistics, how to generate statistics, to being able to critically evaluate the output of AI and others. So it's not so much that they have to do it, it's that they have to be able to recognize it and critically evaluate it. But then the question is, how do you critically evaluate it if you haven't done it? And that, I think, is the question of education under AI, right? If AI doesn't require us to do the thing itself, how are we to develop the critical ability to evaluate the product? And so I'm curious what you think.
Yeah, thank you. So this is a tough question, especially when it comes to teaching students, because we tend to lag behind in our curriculum development and updates. It takes time to change how we teach. And the world of AI, and even in statistics and data science as a discipline, things are changing much faster than we can cope in terms of curriculum development. So this really I think it's a big question. Now, can we teach everything? No. So my view is we have to think about how we can have a diverse view of what to teach, how to teach to different type of students. We won't be able to have a unified curriculum that works for every student. Some students, I think, they still need to learn a lot of mathematics, right? But not everybody. Some students need to learn how to do coding, including vibe coding, obviously, at this time, right? But not everybody needs to do this kind of coding. So if we have enough people who learn more deeply, more serious about certain things, and those people are willing to work together, we solve all the problems. I know this isn't just my wish list.
Let me ask a follow-up to that, just relating it to computer science. So if you go back to computer science, a long time ago now already, 30 years, maybe even more, there were a lot of focus, there was really a focus on teaching this language, that language, et cetera, whatever. And then the pace of new languages started to pick up. So the curriculum evolved to no longer be teaching you this language, that language, et cetera, but to ensure that when the next language came along, it would take you 2 weeks to learn it, right? And so there was a push to understanding certain things, at certain ways that languages had to do things so that, the next language up, fine. So if somebody were to say, looking to take a statistics curriculum, et cetera, but we wanted to create a curriculum so that as things change rapidly, they're not sort of, lost in that change. How do we think about maybe changing the nature of that curriculum so that what you're actually teaching them to do is to be able to adapt to the change that is undoubtedly going to happen?
Yeah, I think that is something that we all have been doing. I think that we all hope to do is like we're teaching students the fundamental knowledge and critical thinking, right? So that they adapt. The real difficulty is things are changing so quickly that how do we know what we are teaching are actually achieving that goal? So I think we need to really learn from students. The best way to measure success is to get feedback from the students, or not necessarily the current students, but recent graduates, right? If we ask them how they are doing in recent, after they finish their degree from WashU, and then use that feedback to help us plan, that will be really better, because we all have the same nice approach and same philosophy in terms of what is critical thinking. What is something that you will be able to use for the rest of your life, no matter how things change, right? But we may not know the real answers. I think we need to be more open-minded to learn from our students, and hopefully that will improve the system. And we have always been doing that. I think it maybe just not enough.
Okay. Go ahead.
Hi, over here. So there are many folks who have expressed ethical concerns about the ethics of AI, There are many people who have expressed concerns about the ethics of AI, environmental ramifications, social ramifications, its applications to surveillance and military technology. And I'm wondering how you, as a researcher and as an instructor when you're working with students, view the balance on teaching the statistics behind AI versus talking about these broader implications.
Yeah, thank you. I know that AI is now impacting so much of our life, our work, and also doesn't come cheaply, right? So a lot of people have concerns, and ethical issues definitely arise. As a statistician, I really care more about, how we make sure that people understand the risks. I think we are not policymakers, or we cannot change in many other ways, but letting people understand how, what kind of risks you actually have, and you have to understand the risks before you fully embrace things. So this, I would say, require our own research. Part of our research needs to directly address that. But also in classrooms, I think we need to integrate, right, a lot of AI-related stuff, say, ethics as an example, into our curriculum. But how to do it is a challenge for all of us. I think if we work together, we will be able to do it. But that's very, very important. Thank you for the comment. Yeah.
We have one last question. One last question.
Well, actually, we have a question. So you have one here?
Here.
All right,
Yeah.
and then I've got a question that was mailed in that I want to make sure we get to.
Okay, great.
Go ahead. So we'll do two questions.
Hello. So sorry for because my question maybe will be so specific. It's about the synthetic data generating you mentioned. I'm curious about, especially you mentioned the correlation between the age and the salary of a person. That is, I'm curious about, because that is example in the social science. So people have, like the AI have a lot of the training data based on the different people, different group of people, different professionals. So they can have a hidden rationale here, and we just uncovered that hidden rationale from that data set. But I'm curious about if that is still applicable for the natural science, for example, in physics or in astrophysics. It's hard to have this kind of a hidden rationale, hidden deep inside of the AI system. So it's hard to. So how can we use the synthetic data in the natural science? Especially you mentioned one of the science paper there. Sorry, this paper may be too specific.
Thank you. Yeah. So I know in some areas it might be very difficult to do good predictions, right, by the AI. And if that's difficult, you may not be able to use the same approach that I'm talking about. But very often, you can talk to people who have knowledge in that area. So if you're talking about physics or biology, there are a lot of researchers in that area. They may be able to provide you some rough idea of how things will work. And those things may be incorporated in the data analysis as well. So it's now I'm referring to this framework of Bayesian statistics, where you use data together with some kind of expert opinion. Maybe that's helpful.
All right, so the last question, and it's sent in, and I'll just interpret it a little bit. So we have a whole bunch of people running around this campus who are first-year students, and we're trying to figure out, okay, what do I major in? So if someone has a choice of majoring in statistics, majoring in data science, or majoring in computer science, how would you have them think about what the approach is to deciding at this stage in their life what they should major in, understanding that things will evolve as they go forward?
Thank you. I assume this was a question from a freshman. If that was the case, I think that person
Probably a
is
parent.
right on track, right? The choice is usually not between one or the other. I think statistics and data science majors are not for everyone, but it's a great option for people who are really interested in knowing why, not just how and what. Also, I think it's really great for people who like to do things, make products, solve problems, not so much in a wet lab, but in a data lab. And could also be a great option for people who like to work with others and who like to be adaptive to the new things. So you don't spend your life working on one particular type of problems. I used to work on swallowing difficulties, and I worked on it for 5 years. I switched to concussion, it was contact sports, and so I then switched to cancer for certain subtypes of cancer and so on. So statisticians have really the benefit of working with many people in many different areas. If you like that, that's a great choice. Certainly I'm not ruling out the computer science. Computer science shares some of the same characteristics, I would say. So as a freshman, I think the first thing is to learn a little bit of math, learn a little bit of coding, right? Final advice, to be a good statistician, or if you like statistics, the most important thing for success is to be adaptive. You have to adapt to changes, and changes is still rapidly occurring.
Join me in thanking Xuming He for just a wonderful event.
Thank you.